Having focused on the carbon cycle, we're now going to switch over and take a look at the global nitrogen cycle. The productivity of many ecosystems on both land and sea is limited in part by the supply of available nitrogen. First, we're going to take a look at the pools of nitrogen on a global basis. So this is the same format as before. This is figure 14.8, and we've done the same thing for carbon, for example. And what we're showing here, if we look in black, are the pools of nitrogen. So as with the other figures, we can take a look at the different pools of nitrogen that we see. And I'm just going to underline these for a second. And then later we'll take a look at the fluxes. So atmospheric N2 is the largest pool by far. The units for these are going to be teragrams, and before, just as before, it's 10 to the 12th grams. And when we're talking about petagrams, a petagram is 1,000 teragrams. So all of these units are going to be in teragrams. And the largest of these pools is atmospheric N2. For the most part, we're going to ignore the size of the N2 pool because it's not reactive, and it's really not a player in thinking about the global nitrogen budget. So ignoring atmospheric N2 and how big that pool size is, let's take a look at these other pools: surface water, deep water, the biota in the oceans, sediments, soils, and vegetation. And there's a couple things to point out here. First is the disproportionate size of sediments. So there's a lot of nitrogen that's stored in sediments of lakes and oceans, and that's a long-term repository for nitrogen. Deep water and surface water, 10 times more nitrogen in the deep water than the surface water, and biota is relatively significant at 450 teragrams. For vegetation, if we think about carbon, the ratio of carbon in vegetation into soils was somewhere on the order of 1 to 2. So there's twice as much in soils. But here we're at 6,500 versus 1,500. And that's somewhere on the order of a 20-fold difference. So now we're at 1 to roughly 20. And there's a lot more nitrogen stored in soils than there is vegetation. If you also remember, it's due to differences in C to N ratios. The C to N ratio of soil organic matter we said was somewhere on the order of 14, and it's 160 for vegetation. So in that sense, we're going to expect that if there are similar amounts of carbon in two pools, vegetation is going to have a lot less nitrogen for a given amount of carbon. And that's why these ratios are so different for nitrogen than they were for carbon. Vegetation has a lot less nitrogen in it per unit carbon. So as far as the major long-term sinks are concerned, it's really the sediments, and the deep water also absorbs a large amount of nitrogen. Vegetation in soils, there's a lot more nitrogen than we have in soils compared to vegetation. And you also notice that there's no nitrogen really here in rocks. Now we've talked a little bit about how sedimentary rocks can have nitrogen in them, and that's a potential source, but for the most part we don't consider that to be an active pool and something that's within the biosphere. So those are the pools, and now we're going to focus in on some of the major fluxes. So as far as the pools are concerned, it was the sediments, oceans, soils, and then vegetation that were really the major pools. Let's take a look at some of these fluxes. From the ocean to the atmosphere, we primarily have denitrification, and that's at 240. Compare that with ocean emissions, for example, and that's relatively low. And other fluxes out, fossil fuel N, animal N, and land emissions. So these, if you take a look at it, 25, 20, 35, are relatively small compared to what the pool size is. In addition, if we start to take a look at land and aquatic denitrification, these numbers start to get relatively large. So we're having a large amount of nitrogen being lost to the atmosphere due to denitrification, land and aquatic systems, and as well as from oceanic systems too. And that's a major source or major loss of nitrogen from these ecosystems. As far as relative importance is concerned for these losses, denitrification is really high up there. But animal nitrogen like ammonia, land emissions are not unimportant because they contribute to this atmospheric pools of reactive nitrogen. Now, as far as the fluxes into ecosystems are concerned, here's deposition, and that's at 90 teragrams. And here's industrial nitrogen fixation at 100 teragrams. So almost as much nitrogen is coming down due to industrial nitrogen fixation as deposition. And when we look at biological nitrogen fixation, that's on the same order of magnitude also. So we're fixing just about as much nitrogen as comes down through biological nitrogen fixation and as through deposition. So as far as the anthropogenic sources are concerned, these are really dominating a lot of the nitrogen cycling. Now, that being said, there's a lot of uncertainty in these numbers. And there's uncertainty with rates of fixation. It's relatively hard to measure fixation compared to measuring carbon uptake, for example. One of the fluxes we didn't talk about is lightning, and there's a lot of uncertainty about how much nitrogen gets fixed in lightning, especially over areas that don't have a lot of anthropogenic inputs. And there's a lot of uncertainty with denitrification. These are hard measurements to make, and we're not certain exactly how much denitrification there is, in part because, as you might remember, some of that denitrification goes directly to N2, and that's a gas that's really hard to track considering how much nitrogen gas is in the atmosphere. So in general, the nitrogen cycle is one of the least constrained cycles at the global scale. There's a lot of measurements that are relatively hard to make. And in that case, a lot of these numbers are probably some of the least certain that we have for global cycling.